Yes, I do. Okay, thank you. Right, so I'm Skye. I work on a SQL database on Hadoop called Impala, and I work for Cloudera. And in short, we use LLVM to do runtime code generation to make your queries really fast. So I'll start by talking about what Impala is and what it does, our motivation for using code generation, and I'll go through kind of how we do the code generation. You can write IR or compile code, and then finally I'll go over some results showing how code generation speeds up our queries. All right, so what the heck is Cloudera Impala? Impala is a high-performance distributed SQL engine for Hadoop. So basically, it's a database that runs on your Hadoop data. For your Googlers out there, it's very similar to Dremel. It's designed mainly for analytic queries, so not so much the transactional OLTP queries, where it's designed for scanning a lot of data and doing complicated analytics on top of that. So since it's on Hadoop, the data is stored in either HDFS or HBase. One of the advantages of Hadoop is that it's very flexible, so you can kind of dump your data in Hadoop in a number of file formats. We support a whole bunch of formats. And then it's schema on read, meaning that after you have your data, you can then define a schema on top of it in order to query it after the fact. And we're very flexible, if you're missing or have extra columns in your data. So you can compare this to a schema on write system, where before you can ingest any data, you have to define your schema. And Impala is open source. At the end of the talk, I'll have a link to the GitHub if you want to check it out. Okay. So our primary goal with Impala is speed. We're trying to run your query as fast as possible, so it's designed for interactive use. So we're trying to run your queries in kind of the minutes to seconds range. And this is where LLVM comes in. We use runtime code generation to create query-specific functions. So it's kind of like it's as if we wrote a function just to execute your query and avoid a lot of the overhead with having a general purpose SQL database. All right, so let's dig a little deeper into the motivation for code generation. What does injecting runtime code information into your functions actually give you? How does this actually save us time? So there's a couple main points. I'm going to go over an example, but in general, we can remove conditionals. So if you have a if or switch statement, but at runtime you know what that conditional is going to resolve to, which branch to take, you can just hard code it. You can kind of in a similar vein, if you have query-specific constants, you can just inline those directly instead of doing a load from memory. And finally, you can inline what would otherwise be virtual function calls or calls to function pointers. So if you know what function you're going to call at runtime, you can call that function directly, and then since we're generating IR, you can run the optimizer and get nice inlining optimizations on the whole compilation unit. So let's go over an example that I think will make this a lot more concrete. Okay, so here's a kind of simplified function from our code base. On the left, you have the interpreted function, and on the right, you have the result of code generation. And I'm using interpreted in a very loose sense here to kind of mean the opposite of a code gen function. So we're not literally writing an interpreter here, but we're sort of interpreting the runtime information as opposed to have it compiled in. So this function is called materialized tuple. Tuple is basically the database term for a record. So this function is reading some encoded record and then converting it into the internal in-memory tuple format. So in this case, that's just a buffer in memory. And so the tuple format, you have a slot corresponding to each field in the record. And so you can see in our function, we iterate through each of the slots, and then each slot has an offset in the tuple, so we look that up to get the slot. And then for that given slot, we know its type, and then you switch on the type to know how to interpret that slot and store it correctly. So we can see that the codegen function is a lot shorter. Let's go into exactly what it's doing, what it's omitting from the interpreted version. So first of all, we're unrolling this loop, which is kind of necessary to get the iteration-specific information. So this, we all know the benefits of loop unrolling. We're getting rid of all the overhead associated with the iterator. We might get better instruction-level parallelism, good stuff. So once we have that loop unrolled, now we can we have this offsets array, which we know is constant across the query. The offsets in a tuple will not change. This is generated at query time based on the format of the data you're reading. So we can just propagate those constants directly. And then likewise, the types aren't going to change across for a given table either. So we can omit the switch statement entirely and just do exactly what we need to do. So you might be wondering, how big of a difference can this make? You know, we're getting rid of some instructions, some conditionals, like my code runs pretty fast and I have tons of if statements. So this function is going to be called for every single record you read, right? So if you're scanning a table that has 10 billion or a trillion or more rows, you're going to be calling this function 10 billion times. And so at this end, the logic is pretty simple. So any instructions you can shave off at this level, especially any conditionals. And like with this switch statement, we're probably going to get a lot of branch misdirection. This is really going to kill you. And we want to kind of shave it down to be as lean as possible, since we're going to be, this is the hottest loop in the system. Okay, so another kind of nice example of where we use code generation, and I think this is just something where code generation is a really great fit, is with user-defined functions, or UDFs. So UDFs are functions that you, the Impala user, can write and then point Impala to, and then Impala can execute them as part of its runtime. So as you can see in the example, you can define some function, my function. It takes one column. You can choose the types. It can take arbitrary arguments of arbitrary types and return whatever type it wants, and then evaluate that on every row you're selecting from your table. So these are just defined as regular C++ functions. We publish an API that you conform to. So with code generation, you can, well, first of all, this is handy. Just even if you compile as native code, it helps us call the function, which is really nice. Since you have that whole arbitrary argument thing, we can generate the signature at runtime in order to call it easily. But also, if you compile your UDF to IR instead of to native code, now we can inline that UDF and also run optimizations over it along with the rest of the machinery that actually calls it. So I have a little picture illustrating this. So here's it's a kind of small, but this is just an example UDF. This is basically what UDFs wrote. I only omitted a few things like null handling. So this UDF is pretty simple. It's just taking the first column or the first argument, timesing by 7, dividing by the second argument. And then so if we select this UDF, and then in a more complicated expression, it generates an expression tree like this. And in the interpreted path, each node in this expression tree is going to have pointers to its children that it will call in order to get the arguments to pass to the function. So as we saw before, this is going to be executed a lot of times. And so having all these function pointers is really going to kill you. Especially in an expression like this, where the actual operations are very simple, the overhead of having those function pointers and calling them is going to be huge. But with CodeGen, we can just inline all these functions. And what's especially cool is that this custom UDF is really treated the same way as our built-in functions, that gets the column from the tuple, that adds it together, and we get a nice simple expression like this that can be inlined and it's going to run way faster. So yeah, UDFs kind of with CodeGen came out very naturally. And another cool thing with UDFs that we haven't implemented yet, but we're pretty excited about is, in theory, since we're working with IR, you should be able to write your UDFs in any language that has a front end that emits LLVM IR. So we're probably going to have to do some munging with the types, but theoretically it should be possible to have Python, JavaScript, Haskell, whatever UDFs, which would be really cool. And they'll run approximately as fast as your native C++ UDFs, since it all gets compiled down to the same thing, hopefully. So we're really excited about that. Okay, so that's sort of what we're doing with CodeGen, the motivation for it. How are we actually performing CodeGen? So in general, you have two choices. If you have a function that you want to have a CodeGen version of, you can either use, or there's probably more ways, but this is what we do. You either use the C++ API to handcraft the IR, so basically writing IR using the IR builder, or we can compile C++ down to IR using Clang. So let's focus on our favorite materialized tuple function again. So we have our interpreted version. We want to make a codegen version. So right now, we use the C++ API to write IR in order to get a function that looks like this. And so I wrote this in C, but it will actually be in IR. I just did this to save space. So this is a simplified version. This is an actual materialized tuple function from the Impala code base. And I don't want you to really look at all the details, just see that it's not terribly more complicated than this. Here's the switch statement, here's the for loop at the very top, and then there's a couple extra things you have to deal with. This is for the Avro format, which is a binary serialization format similar to protobufs or thrift. It's kind of the Hadoop record serialization of choice. So this is the native version, the interpreted version. So we don't benefit from any runtime information here. And then here is the function that performs the code generation to produce IR that we then compile into a function that we call. So you can see this is way more complicated than the native version. Doesn't really share a lot of code in common. And yeah. So, which one would you rather read or write? When you have a bug in this, it's a little bit painful. So, the other choice then is compiling to C++, and I want to take a slight detour into cross-compilation. So, a trick we use a lot in Impala is we'll compile functions both to native code and to IR. And so, the idea with that is the native code is we keep that path, the interpreted path, basically, for debugging. If we do discover, like if one of our customer hits a bug in CodeGen, then they can switch back to the native path, and maybe that will work better. It lets us compare the CodeGen to the non-CodeGen. So it's useful to have the native code around without any CodeGen optimizations. But then we also have the IR version of the same function. And what we'll do in order to kind of turn the interpreted function into the fancy CodeGen function, we'll rip out parts of the IR in the interpreted function and inject runtime information or new function calls that use runtime information into that code. So let's look at an example of that too. So here's another function from the code base. Again, don't worry about the details. Kind of the important point is this is the outer loop driving that materialization of tuples. So we're calling materialized tuple in here. And so we'll compile this both to native code and to IR. And when we run the native code, we use the interpreted version of all these functions. But when we are using CodeGen, we'll take these highlighted functions. So, sorry, let me back up. This function itself doesn't benefit from runtime information. There's no runtime specific stuff in here, except maybe for a few simple things. But it does call functions that benefit a lot from runtime information, like materialized tuple. So in this case, in the CodeGen phase, we can replace these function calls with calls to our handcrafted IR functions that we made. And so this lets us inline those functions and perform optimizations across all of them. And since this is the second hottest loop in the system, it's calling materialized tuple. So you're going to get an iteration for every record that you're scanning. You really want those to be inline and to get the optimizations. So yeah, we use this when we don't have specific runtime information in the function, but we're calling functions that do. So let's go back to materialized tuple again. So this is what we're calling in this function. It'd be really nice if we could cross-compile materialized tuple as well and kind of perform similar tricks instead of having that really awful CodeGen handcrafted IR function. The problem, this is sort of going back to how code generation and runtime information helps us in the first place, is that the compiler is doing things that makes it very hard for us to then go back and inject runtime information. So for one thing, this loop is probably not going to be unrolled because this is a pretty complicated body. And even if we do force it, so if it's not unrolled, then we're going to have to unroll it by hand, and we don't want to do that. So we can force the loop to be unrolled, but then we're still going to have a hard time finding this runtime specific information and identifying what it is and injecting the right value into it. It's just hard to do after the fact. It's easier to do with when you're just writing IR. But, so I haven't implemented this yet either, but kind of my dream is to replace this native code with this special cross-compiled code. So I basically take the parts that are messing up our cross-compilation scheme and replacing them with special macros to be defined. But the basic idea is that, so we have like a macro that says cross-compile for, this one says cross-compile load. So when we're compiling the native code, these macros will just expand into what you see on the left. So that's easy. But when we're cross-compiling, I would like these macros to emit, so I'll have to emit some C code, but then something that will turn into IR instructions that will never actually lower to machine code, but that we can identify later and then pull those out and inject the right information. So somehow, for instance, in this, when we're loading the offset, it will somehow have to be labeled that this is the offset variable. And then in the codegen function, that's going to be munging this IR. It knows, OK, I'm going to look for all the places we use offset and loop through all the offsets and just plug in the right numbers. So if anyone, I'm not sure exactly what that's going to look like yet. Probably something kind of hacky, like this might be a function call with a magic symbol containing offsets that I'll search for and then replace. So if anyone has any clever ideas for how to do this, I would love to hear it. Because this is a lot simpler and more elegant than writing a huge separate code gen function. It makes debugging easier because you can run a native code and it more closely resembles the code-generated code, and it's just easier to write. So this is sort of the dream. OK, so that's what we're doing with code gen. The question is it worth it? Do we actually see improved query times for all this work? And the answer is yes. So in this chart, I'm comparing a couple different queries, and I'm running them in the interpreted with no codegen versus the codegen path. So you see in blue, we have without codegen. With orange, we do have codegen. And I'm running 3 different queries. So the queries go from least to most complicated. So you can see, as we get more complicated queries, we can benefit more and more from runtime information, and we see more impressive speedups. So this first query over here is just a simple select count star. And so in this case, we actually don't even need to parse the records. There's record counts at the beginning of each block. So the only codegen we're doing is an aggregation here. And that already gives us a 4 times speedup. So once we do a count over a specific column, now we actually need to parse the records to see if that column is null. And that bumps us up to a 6 times speedup. And the last query is a TPCH query. It's TPCH Q1. TPCH is just a kind of commonly used database benchmark used for these analytic databases. I didn't put it on this slide because it's extremely complicated. But as you can see, there's a lot going on here and a lot of places we can use codegen. So all the expressions, each one of these can benefit from codegen. In particular, we can also do sub-expression elimination. So we have expressions like here, 1 minus discount. So we can copy that. But also, even when you just have the same column referenced more than once, it is a bit of work to pull the column out from the in-memory tuple. So we can even eliminate all the subsequent uses of that column. We already know the value. And since it's all inlined, that should just work. Similarly, we have this predicate that can be cogened. In some cases, we can get really fancy where if we can evaluate the predicate first, then we could skip parsing the rest of the columns that come after the predicate column if the predicate fails. And then the group by, that's basically an aggregation. So we also get cogen here. So cogen everywhere, and it works really well. So diving kind of into this query, I also ran this query just on my desktop and ran perfstat to get some extra numbers. So this is the same query. You can see the speedup isn't quite as impressive. I think this is because I'm working on a much smaller data set. This is about 3 gigabytes versus 40 gigabytes on a cluster. So I didn't look into it too much, but basically the overhead you get more overhead when you're working with a smaller data set. Kind of the bigger your data set, the more these optimizations in the hot path will help you. But you can see that, so we have like about a 4.3 speedup. The number of instructions is cut, And probably more importantly, the number of branches is cut. So as we saw before, branch misprediction and pipeline stalls are really going to kill you. And so this is more reflective of the speed up we see. So that's very important. So the final slide I have, I stole this from a coworker's deck. So unfortunately, I don't have the cluster information, but I know he was running on a 10 or 20 node cluster on a non-trivially sized data set. And he's running all the TPCH queries and comparing Impala against another SQL on Hadoop system. So unfortunately, due to weird legal reasons, we actually can't tell you which system that is. You're not allowed, most like major databases have a clause in their user agreement that says you cannot publish benchmarks of that database without their permission. So some unnamed database, but you can see that we're doing pretty well against them. There's a couple queries where we don't do so well, but in general, we're keeping up with at least some of the competition. And as we saw before, CodeGen plays a huge part in this. So if we didn't have CodeGen, then we might be 16 times slower, and then we wouldn't be doing so well. So I think this really speaks to what a powerful technique this is. Okay. That's all I have. I still have a lot of time left, but if anyone has questions, suggestions, is what I'm doing totally silly or totally cool, I would love to hear about it.
Just a note, IBM DB2 does not have Divids clause.
Does not have what?
Divids clause.
Okay, well that eliminates one possibility then.
Yeah. Anyway, I mean, you could have compared IBM DB2. Anyway, so the question is like generally in the database world, it's always like considered that IOs are like very expensive than CPU. Whenever you go and talk to a database person, he says, don't worry about like the number of instructions executed because IO time dominates everything else.
IO dominates?
Yeah,
okay.
IO dominates everything else. So like in your charts, like the speedups look very impressive so that it is like, it convinces me that like IO is not dominating, then CPU is dominating. So like, do you have some sort of measurements about what was the IO time versus what was the CPU time?
Right, so in most of these charts, we actually, like you'll see that the database, or it doesn't quite fit in, will it fit in memory here? It depends on how much space we're taking with our services. But we run it a bunch of times so that most of the data is in the OS buffer cache, because for these numbers, we don't want the IO to mess them up. But in general, so you're right, in many cases, isn't as important because IO will dominate. On the other hand, many people do run with small enough working sets that your data will be cached. And also we're seeing in one of the file types we support is Parquet, which is a columnar format loosely based on the Dremel format. And at least with Impala, we're seeing that when we're reading Parquet files, we are CPU bound, because it's just more efficient than, say, a text file.
But it's not just this, it's that when you optimize your constraints on your query, you're actually avoiding a lot of I/O because you're grouping first, or you selecting, or you're filtering first.
We can do that in some cases. In many cases, we can't. Just like in the case of Avro, which is what I ran these numbers on, you sort of have to parse the whole record, even if you're throwing most of the columns away, because they don't have fixed-sized fields.
Yeah. But that's a bug in the database, not in your.
I mean, it really depends, but we see that you're not always I/O bound, and especially with these really complicated queries, the CPU time is going to become more and more important.
Generally, if you have like sort is the only operation which is generally like CPU bound in a SQL. I mean, in any query, right? Like, if you're not doing sorting, if you don't have a sort in your like query plan, like the generated query plan, there's nothing which is really CPU bound.
I mean. That might be true in some cases, depending on your data. We definitely do not see this all the time, especially with a columnar format. So
first of all, it's really cool.
Thank you.
When you say Hadoop, that's kind of an overloaded term. Do you mean HDFS specifically without any of the Hadoop infrastructure over it?
Yeah, let me go back to that slide.
Oh, I missed it.
I thought I was going to run out of time, so I went through what we do really, really fast.
Okay. That kind of answers
yeah.
my second
Right.
question, which was, I mean, how does the JVM interact with LLVM? And in this case, I guess the answer is it doesn't.
Right. Okay. So I should clarify that Impala, it's written in C++, first of all, and we don't. Up until now, I guess the core of Hadoop has been MapReduce. That was everything boiled down to that in terms of processing. Impala is an entirely new execution engine built more like a traditional SQL relational database. So it's a new execution engine that does not depend on MapReduce at all. So the storage is still HDFS or HBase, but the execution engine is Impala.
Cool. Thank you.
Is there a security model for generating code and executing it in process with your database?
For UDFs, you mean?
For any case where you're generating code, and if the query was malicious or something, it could cause you to generate buggy code or something, and then you execute it and everything blows up.
Right. So since this is an analytic database, we're not really worried about like SQL injection, because you're probably not putting this in front of a web server. It's more for you're sitting at a terminal, you're a data scientist exploring your data, or you're a business analyst using a BI tool or something. So Impala does have a security model we just introduced called Sentry that lets you have table and database-based permissions. That's sort of orthogonal to CodeGen. That's at the access level. As far as UDFs, right now, there is no security model for that. We just introduced them. I think it's kind of use at your risk if you point Impala at a virus and run it. Sorry, don't do that.
Thanks.
And you should have filtered the input before.
So I was curious how many things you sort of did at your mid-level IR, basically, if you want to call it that, your parsed SQL statements and such, versus just sort of let LLVM's constant folders and common sub-expression elimination go at it. Like
right.
for the last query you showed, did you hand roll a bunch of constant sub-expression elimination, or do you just sort of say, and then we ran the hell out of the LLVM passes there, and it just worked?
We do have an explicit. We did write our own our sub-expression elimination pass, and I actually don't know off the top of my head why we couldn't use the built-in one. I didn't write that function, but there was some reason. In general, we do mostly rely on LLVM's passes. We do the runtime specific information because obviously LLVM doesn't know what's specific to the query because it just looks like an array that could be volatile.
Yeah. Sort of as a follow-up, I was curious if I feel like some average deviation, like a lot of these examples, like do you guys do anything fancy there as well? It's sort of like if you're computing the sum and the average and the deviation, those all fall out really easily by keeping something around on the side.
Right.
You guys try and do something fancy with that, or are you just sort of, the big win is just computing them with x86, not with an interpreter?
Right now we don't. Actually, all this code I showed you, I was talking about how UDFs are run the same way as expressions. None of this code uses that. We use, right now the built-in expressions are basically handcrafted IR. We're in the process of kind of moving everything over to this cross-compiled model and writing more expressions as UDFs. And I think once we have that model, it's a lot simpler to reason about, and maybe, hopefully once everything is inlined, the compiler can figure out we're reusing variables and do clever things like that.
Thanks.
So this is just a clarification. Do user-supplied UDFs, are they in C++? Do you have the source to them, or are they sort of compiled?
They're pre-compiled, so you can either compile them to shared libraries, in which case we'll just dynamically link them and call them, and you get that overhead, or you can supply a generated IR, compile it directly to IR, and then we'll load that into our module and inline it and everything. So when you register the function with Impala, you have to give us the signature, and that's how we know how to call it.
Yeah, because you mean if you don't have the LLVM mirror to it, then you can't inline, that example won't work.
Right, right. Yeah, so we do have an option for just a shared library, which is kind of I think how most databases work, so people are more comfortable with that. But if you want this added boost, then you can compile with IR. But with Clang, it's basically, you add an extra flag, and then that's that.
Okay, thanks.
I do have a question.
Okay.
It's more about the file system than the LLVM side. As you said that you have these variable length records. So in the past, what I did in this is just separate the fixed length from the variable length, and you split because you're probably using the HFS to have a distributed file system, right?
Right.
That's the main reason to use that. And then if you're going to run these things, you can then separate per machine because you know what data is in each one of them. So you don't have data locality and all these things.
Right.
So if you have a fixed length, you can, for instance, you showed in one of the first graph is like a count star. Yeah, that one. That's an op because you know how many records you have because you have the number of all the fixed length records in one side and all the variable length record on the other side. And then you can calculate automatically the size of the table by just one minus the other or something like that in each block. So if you separate these things, you can actually make all of this almost flat.
Right. So unfortunately, most file formats don't do this.
Yeah, that's
and kind of part of the appeal is that we let you use whatever file format you want. So if you are going to convert your data to a specific format, we suggest everyone use Parquet, which is the columnar format I was talking about. And then you get awesome performance. But if you're kind of just generating data, it's probably easier to do a non-column-based format. But yeah, that would probably work too.
Anyone else? So, thanks.
Thanks a lot.